In the few seconds it takes you to read this sentence, a system at LinkedIn just swallowed millions of events. Clicks, searches, profile views, part of the trillions it handles every single day, and almost none of it is ever lost. That system is Kafka. And here is the strange part. It is not fast because of some genius algorithm. It is fast because of one stubborn rule. So simple, it almost sounds like a mistake. Never change the past. Only ever add to it. Stay with me for 10 minutes and you will understand Kafka better than most engineers who use it every day. And you will be able to prove it in any system design interview. Let us rewind to before Kafka existed. Picture a company with just a handful of services. Service A needs data from service B. B needs something from C. Easy. You just wire them together directly. But now let that company grow. 30 services. And each one needs to talk to 5 others. Suddenly every service has to know about every other service. It is like an office where everyone has everyone else's personal phone number and nobody can stop calling. One service goes down and messages just vanish. Traffic spikes on one team and the whole thing topples over together. Engineers have a name for this. They call it the spaghetti mesh. And around 2010, LinkedIn was drowning in it. Billions of events a day and nowhere clean to put them. So they reached for an old idea, the message broker. Instead of wiring everyone to everyone, you put one thing in the middle. Think of a bulletin board. A producer walks up and pins a message to the board. And whoever cares walks up and reads it. The sender does not need to know who's listening. That is called decoupling, and it is the whole game. There was just one problem. The popular brokers back then, RabbitMQ and ActiveMQ, behaved like a vending machine. You take the snack, and it is gone. One consumer grabs a message, and no one else can ever have it. You could not replay it. You could not let 3 different teams read the same data. So Kafka asked a better question. What if the board worked less like a vending machine and more like a newspaper? Printed once, read by millions, and still sitting on the shelf tomorrow. So how do you build something that remembers everything and still keeps up? You start with the simplest data structure in all of computer science, the log. Now, forget error logs. That is not what we mean. A log here is just a notebook. You only ever write on the next empty line. You never erase. You never scribble over an old entry. Each line gets a number, which engineers call an offset, and those numbers only ever go up. This sounds far too basic to matter. It is actually the secret to everything. Here is why. Think about how a hard drive physically works. To write to a random spot, a tiny arm has to swing across a spinning platter and find the exact position first. It is like a librarian walking the entire building to file one book in its precise alphabetical slot. Make her do that hundreds of times a second, and she spends all day walking and barely shelves a thing. That is a random write, and a spinning disk manages only about 100 of them per second. Now picture her simply dropping every new book onto one growing pile by the door. No walking, no searching. That same disk, writing in order, pushes around 100 megabytes every second. That is not a small gap. It is 3 orders of magnitude, roughly 1000 times faster. Same disk, same hardware, wildly different speed, because Kafka only ever appends, it gets that speed for free, and it gets something else too. When you never change old data, you never need locks. No 2 writers fighting over the same record. No fragile bookkeeping to keep an index in sync, because the log is the index. One stubborn rule, never change the past, and half the hardest problems in databases simply disappear. One notebook is wonderful, until it is not. A single log lives on a single machine, one disk, one network card, one CPU. Eventually, it maxes out, and Kafka's answer is beautifully simple. If one line is too slow, open more lines. Picture a supermarket at rush hour with a single checkout open. The queue stretches to the back of the store. What do? You open more lanes. The crowd splits, and everyone moves faster. In Kafka, those lanes are called partitions. A topic, say user clicks, is not one log. It is split into many partitions, spread across many machines, all taking messages at the same time. Need more throughput? Open more lanes. But here is the part that makes Kafka really click. Each lane gets exactly one cashier from your team. That is a consumer group, a set of workers that splits the partitions between them with one rule. No two of them ever touch the same lane at the same time. 8 partitions, 8 workers, 8 streams flowing in parallel, nobody stepping on anyone's toes. And every worker keeps a bookmark, its offset, so if it crashes and restarts, it picks up exactly where it left off. Nothing lost. Nothing read twice. Now for the real magic trick. That same stream of clicks can be read by completely separate teams at the very same time. Your analytics team, your search team, your fraud team. Each one is its own consumer group, each with its own bookmark, none of them even aware of the others. One newspaper, and every department quietly reads its own copy. That single idea is what finally killed the old tangle of point-to-point wiring. Here's a chapter most engineers have never even thought about, and it is the one that makes interviewers lean forward. When a normal program sends data from a file out to the network, that data takes a surprisingly clumsy journey. First, it is copied from the disk into the operating system's memory, then copied again into the application, then copied into a network buffer, then copied out to the network card. 4 copies of the exact same bytes, just to send them once. Let that sink in with the picture. It is like needing to mail a single letter. But first you photocopy it, then you photocopy the photocopy, then you photocopy that 4 times before it finally drops into the mailbox. Every copy burns time and processor power doing nothing useful at all. Kafka refuses to play that game. It uses a special instruction called sendFile, and sendFile tells the operating system one simple thing. Take the data straight from where it already sits and hand it directly to the network card. Skip the detours. 4 copies collapse down to almost none. That is what people mean when they say zero copy, and it gets even better. Remember, Kafka's readers are usually reading messages that were written just seconds ago. Those messages are still sitting in the computer's fast memory, called the page cache, warm and ready. So Kafka often never touches the slow disk at all. Sequential writes flowing in. Warm, zero copy reads flowing out. That combination is how one single Kafka machine can push hundreds of megabytes every second, while barely breaking a sweat. Speed means nothing if your data vanishes the moment a server dies. So how does Kafka stay this fast and still never forget? The answer is copies. Every partition has one leader and a few followers. The leader does all the real work. The followers quietly copy everything it writes, line for line. Think of a lead singer and her backup singers. The backups follow the lead note for note, always ready to take over if a microphone suddenly cuts out. But here is the clever bit. If a backup singer drifts badly out of time, you bench her. You would never hand the song to someone who has fallen behind. Kafka does exactly this. The followers that are keeping up are called the in-sync replicas. Fall behind, and you're quietly dropped from that club. And when a leader fails, only a replica that was truly in sync is allowed to take the stage. So you never, ever recover from someone holding stale data. Now, Kafka hands you a dial. When a producer sends a message, it can ask for different levels of proof. The fast setting, the leader says, got it, the instant it writes. But if it dies a split second later, that message is gone. The safe setting, called Axol, the leader waits until every in-sync copy has the message before it confirms. That costs you just a few milliseconds, and it buys you a promise. You can lose an entire machine and not lose a single message. Fast or safe. You turn the dial yourself, and that exact trade-off is something interviewers ask about constantly. Quick question. If I told you an account balance went from $1,000 up to $1,200, do you really need to keep that old number forever? Sometimes yes, but often you just want the latest. Kafka can throw data away by time or by size. Delete anything older than a week, for example, but it has a third, smarter mode called log compaction. And here is the whole idea in one image, your phone's contacts app. It does not store every phone number a friend has ever had. It quietly keeps the most recent one and drops the rest. Compaction is Kafka doing precisely that. For every key, keep only the newest value and sweep the stale ones away in the background. Think about what that unlocks. A service that needs the current balance, not 6 months of transactions. A product page that needs today's price, not its entire pricing history. A leaderboard that needs each player's best score and nothing else. The log stays lean, while the part that matters is guaranteed to survive. And here is the beautiful twist. A compacted log is functionally a database, the latest value for every key, distributed, replicated, and fault-tolerant. And you did not bolt a separate database on to get it. You simply let the log quietly become one. So you understand Kafka now. Let us turn that into something an interviewer cannot ignore. Because here is the secret. Most candidates can describe what Kafka does. Almost none can explain why. And that gap is exactly where you win. They ask, how does Kafka handle such high throughput? You do not just say it is distributed. You say sequential disk writes, a warm page cache, and zero copy transfer using send file. 3 layers deeper than everyone else in the room. They ask, how do you scale it? You say, add partitions, then add consumers to the group, up to 1 consumer per partition. Need more independent readers. Add another consumer group. No coordination, no contention. They ask about not losing data. You say, Axol, with a minimum of 2 in-sync replicas. Strong durability, just a few milliseconds of cost, and your magic word. It is tunable, not fixed. They ask about ordering. You say, Kafka guarantees order inside a partition, but not across them. Need one strict global order? Use a single partition, but you trade away parallelism. Need order per user? Hash by the user's key. So all of their messages land in the same partition in order. And then the one that trips up even senior engineers. How does a brand new service replace 6 months of history? You do not copy a thing. You simply start a new consumer group at the very beginning and let it read forward at its own pace without touching anyone else. That answer right there is the difference between someone who reads the documentation and someone who genuinely gets it. That is the whole picture. The append-only log is the foundation. Partitions are how it scales. Zero copy is how it flies. Replication is the safety net. Consumer groups are the fan-out. And compaction is the bridge from a stream to a database. One rule, never change the past. And everything else just falls out of it. If you made it all the way here, you now understand Kafka at a level most engineers never reach. And it all grew from one stubborn little rule. Next, we tackle how distributed databases agree on the truth, even when servers fail and networks split apart. It is the consensus problem behind every system you trust with your data. Subscribe, and I will see you there.